Today we are entering into ninth part of Introduction to Computer Control of Processes. This is my 14th webinar, 17th April. Velocity, yesterday we stopped here, velocity form of PID controller. The difference, the main difference between velocity form and position form is position form means it gives total controller output. Total controller output. It can directly given to the final control element. DAC, then it can be given to I to P, then valve like that. Or it can be directly given through DAC, it can be directly given to VFD like that. But on the other hand, if it is a velocity form, it gives how much increment that is from previous controller output and this controller output. That is velocity form. In the velocity form, how we are finding that, we'll find the controller output at nth sampling instant. That is Kc multiplied by nth sampled error. Then we have to integrate up to nth sampled error. That is integration is summation is from k to n. And derivative also the difference between present error and previous error. So here the constants are Kc T by Ti. Here constants are Kc Td T. Kc is common. Here the constant is Kc. The same way we can find for n-1th sampling instant. Wherever you find n, you have to replace by n-1. That's all. Now you subtract this from this, you will get the change in controller output, because this is n-1th controller output, this is nth controller output. We got, if you find the difference, you will get this. So how we wrote all the first term, where and all we are finding E of n, here 1 E of n, here 1 E of n, here 1 E of n. That's all. Here up to n-1 only. If you subtract this from this, here also the summation up to n-1 is getting cancelled. Therefore, only this is Kc T by Ta into E of n only. So, what are the, how many terms? Only 3 terms. If you write the 3 terms here, what is the coefficient? Kc only for first term. Here, Kc Ti by Ti. Here, what is the coefficient? Kc Td by T. So we wrote for E of n, the first term for change in controller output. Second term, we have to consider all n-1 terms. Where and all n-1 term? Here it's there, here it's there, here it's there. Here it's not there. It is getting cancelled while adding with that only one term, that is En alone is there. That's why this is also getting cancelled. This is also getting cancelled, and En alone is there. So only 3 terms. What is the coefficient of this Kc? That's why the Kc. What is the coefficient of this? Here minus sign is outside, because we are subtracting this from this. That's why this is all terms plus, here all terms minus. That's why minus outside. Kc alone is there for this. For this, Td by T, Kc Td by T E of n. Here plus, because this is minus, this is also minus. That's why if you put plus, the outside minus will give that minus sign. So Td by T Kc E of n-1. Here also one more term, the same term with the minus sign outside, So 2 times you will get. So this also we wrote. The third term, how many n-2 terms? The error sample that how many n-2 terms now we have to see. This is n-, this is the only n-2 term. here one minus is there, here one minus is there, another minus is in the outside. That's why plus Kc Td by T E of n minus 2. So if you take E of Z, take Z transform and bring E of Z to the left hand side, you will get the pulse transfer function for controller. So here E of n, that becomes E of Z. That E of Z we brought here. And here E of n minus 1, that's why E of Z. For n minus 1, that's why Z power minus 1. We kept that Z minus 1 here, and E of Z we brought here. Here E of n minus 2, that's why E of Z power minus 2. So we brought that E of Z here. That's why this is the transfer function for pulse transfer function for PID controller. Now, what are the advantages of velocity form that we'll see now? There are three advantages. Three advantages we'll see one by one. The first advantage is there is no integral wind up. What is integral wind up? Integral wind up is if any persistent error is there, then integrator will continuously integrate that error and the controller output will saturate at one point. The error is exist for a long time, then the controller output will saturate because of integration. So there are two parts already we have seen. There are two parts. One part is the integral. That integral output is coming out as controller output, but the controller output is limited to 100% only. That's why internally the integral output may exceed beyond 100% because of persisting error. The error is continuously existing. That's why it may go beyond 100%. That is called integral wind up problem. That we learned how to solve that problem in continuous domain. Already we have seen that. Here also the same problem may come because here integral instead of integrator, the summation is there. It continuously adds the error. That's why the error will be continuously added, and the controller output may exceed 100% because of that. Suppose the error is reversed, then what will happen to summation? It will go on decrease the controller output, but it already integrated beyond 100%. Beyond 100%. That's why, valve will open 100% only. Suppose the control output is 120%, valve is open only at 100%. That's why, if the error is so far it is positive, now the error becomes negative. So it starts from 120 only. So to reach 100, it takes some time. Then only the controller output starts decreasing. Suppose if we stopped at 100% exactly the controller output, then the valve will completely open, and the integration also stopped at the point. Means whenever the error is reversed, it starts from 100 itself. So immediately it starts decreasing. That is called solution for integral wind up. Here, if you use push velocity form, there is no summation there. That's why no integral wind up problem. That is the first advantage. That is the first advantage. No integral wind up problem. Second problem is, second advantage is, here if you see the position form, and the position form, it will be plus some initial value bias. Here plus bias. So if you subtract bias getting cancelled, but bias is not required because it always added the previous controller output in its output. That's why there is no initial value required for this. There is no need of bias required. Automatically it is included in that. Bias is automatically included because the total controller output equal to previous controller output plus change in controller output. So bias is automatically included in the control algorithm. That's why there is no need of bias. There is no need of bias. Initialization not required. Initialization not required. That is second advantage. The third advantage is process computer failure. Computer failure means computer failure means in this case the computer failure means there is no controller output. There is no controller output. It protects the process against computer failure means it is not giving total controller output. It will give only incremental value. That's why the controller output outside is integrated. It is added to the previous value. That's why if the controller doesn't give controller output means the final control elements will be stopped at the previous value. That is safe. That is the third advantage of velocity form. And one more point here mentioned is the tuning methods for this PID controller. We can use the same Ziegler-Nichols, Cohen and Kuhn. The same can be used here appropriate with the appropriate sampling period. Sampling period must be minimum as much as possible. If it is very, very small, then it looks like a continuous system. So all those techniques can be applied here. That's all. To explain this, once again, I explained this. Once again, I derived that transfer function only to explain on these 3 points. So if I directly tell, it won't look nice. That's why I said. Now, effect of sampling. Now let us find what is the effect of sampling on the controlled output. Let us see. The controller output will be like this. It will give at the 0th sampling instant, gives control output. At the first sampling instant, it gives controller output. Second sampling instant, it gives like this. Third sampling instant like this. So the in-between sampling period, it doesn't give any control output. That is the meaning. It means what? The controller doesn't control the control system means the system is in open loop. The system is in open loop. In other words, the loop is closed only at the sampling periods. Otherwise, it is at open loop. It is only at the sampling instance it is closed. Otherwise, it is in open. So, when the thing is during sampling interval, the controller controls the process using old. So, in the sampling interval in between these two, what is the controller output? Whatever value given at 0th sampling instant will be maintained up to next sampling instant. At first sampling instant, whatever we got will be maintained till next sampling instant. Whatever value we got will be maintained for till next sampling. Whatever we got will be maintained for next sampling instant. That's why the in between two samples, the controller output is old value, not the current information. These are the effect of sampled output. Effect of sampled output. One more thing is already we have seen that the sampling period should be appropriately selected. For large sampling period, the system may become unstable. Yesterday we have seen. That's why for flow process, it is recommended that 1 second. For level and pressure, sampling period is 5 seconds. For temperature, very slow process, that's why 20 seconds. These are all recommendations, not rule. You can select based on your process time constant, you can select like this. But anyhow, generally we can say that for flow, very small sampling period because very small time constant, fast process. Moderate speed, that's why it has 5 seconds. This is very slow, that's why 20 seconds. Another important thing about sampling is there is a phase shift in the process because of sampling period. That how we will see that. So here you see here you see here you see here the output is sampled at this point. So up to this point, the controller is varying like this and reached this point. But we are not sensing that value, and we are suddenly sample this. So output is higher value. That's why we are going here. Similarly, if it is a continuous system, it will vary gradually like this. But what we are doing, we are waiting till next sampling period. Then suddenly we got the new value. So it means if you draw the waveform, for this, you look here. You look here. It is this is continuous output. What is the sampled output? The sampled output is it comes like this. So if you see, compare these two up to this. Continuous means the earlier we got. Sampled means we are getting after some time. Therefore, that is a lag, delay in the process output. Delay in the process. Here also you can see the same. You can see the same here also. Here, this is the continuous output. But the sampled output comes after some time. After some time. You see that the here it comes. This is continuous. Here also you can notice that the sampled value comes after some time. That's why the entire output is shifted to the right. The entire output is shifted to the right. That's why there is a delay. Dead time is introduced by sampling period. There is a dead time is introduced by the sampling period. Different class of digital controllers. Now we analyzed the response of digital control system, closed loop response of digital control system. Now let us see how to design different class of digital controllers. Analog controllers, we have seen one analog controllers, that is PID controller. We have seen other controllers we didn't see. In the same line, we designed a digital PID controller also. That also we know. In addition to that, because of computing facility, we can design many controllers, digital controllers. That we will see one by one. As a first thing, we are going to see what is the expression for digital controller. That we will see first. Then we will see how to design a deadbeat controller. Then we'll see how to design a Dolin's controller. Then we'll see how to design a Kalman's controller. Those things we will see. Then after seeing Dolin's controller, we are going to see what is ringing effect. Then with respect to performance, what is the difference between deadbeat controller and Dolin's controller? That and all we are going to see. First, let us derive the controller output. We know that this is the controller response, servo response. This is servo response. Servo response. It means we are assuming that D of S equal to 0. Disturbance equal to 0. If you assume disturbance equal to 0, then what you will get, what is the forward path transfer function? Forward path, what and all there? D of Z is there in the forward path. That is the controller. After that, GP of Z is there, but it should presided by hold circuit. That's why the forward path HGP of Z is there. What is in the loop? In the loop, forward path HGP of Z, D of Z. In the feedback path, nothing is there, only unity feedback. That's why the loop transfer function is same. HGP of Z, D of Z multiplied by feedback equal to 1. Therefore, the closed loop transfer function is 1 plus HGP of Z, HGP of Z, HGP of Z, D of Z. We got here. It is general practice that we are putting other side. Right. Okay. So this is the servo response. Servo response means what? Output by output y of z equal to this. By input, what is input? Input is here in a closed loop system set point. Set point is the input. Y set point of z. So if you bring that set point to the right hand side, you will get the response, step response, or change in for change in set point. This is the response. This is the response you will get. Now let us find let us find the controller d of z from this servo response. For that, you bring again this y of z to the left hand side. You will get y of z upon y set point of z. Y set point of z. So I brought this y of z, y set point of z to the right hand side, and this denominator also I am bringing to the left hand side. After multiplying that y set point of z, dividing that y set point of z to the left hand side, or you can directly take y of z by y set point of z as d of z. So that I brought, then I am bringing this denominator to the numerator. So if you bring that, what you will get? 1 plus h gp of z, gp of z, d of z. You will get. What is the right hand side? Right hand side, you are having hgp of z. Right hand side, you are having hgp of z, d of z. That's all. So now you bring all d of z one side, and the remaining things one side. What you will get? Y of z, y of z by y set point of z, y set point of z multiplied by 1, this 1 equal to what you are getting. Already in the right hand side we have hgp of z, hgp of z in the right hand side multiplied by d of z we are having in the right hand side. This you can, this plus term can bring to the right hand side. If you bring this to the right hand side, minus, you will get a minus. What you will get? Y of z by y of z by y set point of z, y set point of z, h gp of z, h gp of z, d of z. That you can bring to the right hand side. So if you take that d of z outside, what you will get? If you bring that in the right hand side, if you bring the d of z outside, outside, what you will get? This is only hgp of z, hgp of z, hgp of z minus, what is here? Y of z by y set point of z, y of z upon y set point of z, hgp of z, hgp of z. That you are getting. Therefore, d of z equal to, therefore we can say that d of z equal to, from this we can write that d of z, you bring what is in the left hand side? Y of z by y set point of z. So that is in the numerator, y of z by y set point of z. That is there in the left hand side. That you can notice this term that we wrote here, divided by whatever you are having here, you can bring here. Before that, you can write hgp of z is in both terms. That's why you can separate this hgp of z separately. hgp of z can be taken outside. What is the remaining thing? 1 minus y of z by y set point of z. Y of z by y set point of z. Y set point of z. So that's what that is you got here. So what is d of z? D of z equal to 1 by hgp of z, y of z by y set point of z divided by 1 minus y of z by y set point of z. Whatever may be the controller, this is the digital controller output. Here, what and all given to design a controller, whenever you want to design a controller, you need the mathematical model. Mathematical model of the process is required. Without knowing mathematical model of the process, it's not possible to design the controller. To design the controller, we need the mathematical model of the process. That is one thing. Second thing is we need a constraint. For that constraint, we have to design a controller. So here, one is we need the mathematical model. If mathematical model is given, then we can find HGP of Z. We can find the HGP of Z. That's all. That part is over. Then what is the constraint? The constraint here is the controller is designed for servo response. That's why y of Z should track y set point of Z. So here constraint, we have to tell what type of constraint we want to take. If we tell that, then we can find d of Z. So if you know HGP of Z and the constraint y of Z by y set point of Z, if both we know, we can design the controller. You see the controller once again now. What is the controller? The controller is d of Z equal to 1 by HGP of Z. This is nothing but a model of the process. Model of the process. Suppose I do not know the model of the process, but I'm having a process that has to be controlled. Means what you can do is you can give step change to that. Then you will get a reaction curve here. Then you can model, you can find the dead time here. This is the dead time for which there is no response after giving input. Then you can find the time constant after dead time taken to reach 63.2% of the final value. That time taken, that is time constant, you can find TP. Then you can find the ratio of output, change in output by change in input. Earlier it is at 50%, now it goes to 55% for 5% change in controller output, 5% change in controller output. Therefore, Kp equal to change in process output, 55 minus 50 divided by change in controller output. Also, by earlier controller output is 40% at the nominal operating point. Now it becomes 45. Therefore, 45 present value is 45 minus 40. Therefore, 5% change in output for 5% change in input. Therefore, 1% per percent. Why I am telling this is always you should consider the process output while designing the controller. The process output should be considered in percentage only. Then only you will get correct tuning parameter. If you suppose it is a level process, if it is a level process, in that level process, the level is varies from maximum level is 4 feet. 4 feet. The flow rate is 2 liters per minute. Inflow rate is 2 liters per minute. Outflow rate also will be 2 liters per minute. 2 liters per minute. What is the gain of the process? If you asked Kp, if you asked what is the gain, you will get Kp equal to, suppose I am giving 1 liter per minute change I gave. Therefore, change in level is 0.5 feet, 0.5 feet or 0.5 feet. And the change in output for 1 liters per minute change. Therefore, 1 liters per minute is changes. 1 liters per minute is changes. Then what is the controller output? 0.5 feet per liter minute. So this is the unit. So this is in inches. This is in feet. This is in liters. This is in minutes. If you combine all these together, then what is the controller controller gain, unit of controller gain? It will be opposite to this always. So to make it unitless controller output, the controller output must be so many liters, because it manipulates inflow rate. So many liters per minute, per feet, like that it will come. So per feet, like that it will come. So here the controller gain will be in engineering unit, means it is very difficult to find. That's why we have to see everything in percentage controller output. That's why always you get clash with the chemical engineers. As far as instrumentation engineer is concerned, you will see the process 0 to 100%. That's all. But chemical engineer won't look like that. He will see in terms of engineering units. That is correct. They should see like that only. But instrumentation engineers should see the process output 0 to 100%. That's all. He has to control at 50%. The span is 0 to 100%. That way he has to see whether it is temperature or level or flow rate, whatever it may be. He should see it is a percentage only. One temperature process from 0 to 3000 degrees centigrade. It has to be maintained at 1500 degrees centigrade. Total span is 0 to 3000 degrees centigrade. It should be maintained at 1500 degrees centigrade. Means its set point is for chemical engineer it is 1500 degrees centigrade. For instrumentation engineer 50%. On the level process, it's of 10 meter height level process. It should be maintained at 5 meters always, because total span is 0 to 10 meter. So 5 meter corresponds to 50%. For an instrumentation engineer, for that also he says 50%. That's why the whatever chemical engineer says, instrumentation engineer may not be able to understand, but he must understand. But he should perceive as if he is an chemical engineer. But after that, you should work on percentage. Why I'm telling this is you should see the controller gain, controller output, process output, error, everything you should see in percentage. Then only you can tune any process. Otherwise, you will be in the. That's why we should see everything in percentage. Now let us move on to design of controller, deadbeat controller. To design that controller must be physically realizable. Must be physically realizable. What is physically realizable, that we have to see. Physically realizable. Physically realizable means what? This is the controller output. Once you designed the controller will be a polynomial in Z. Denominator and numerator polynomial will be in Z. That's all. This is a controller output. It has some polynomial in the numerator, polynomial in the denominator. That's all. So this is the controller you have to employ. But we do not, once you designed that controller, we do not know whether it is physically realizable or not. How to find whether it is physically realizable or not? How to find whether it is physically realizable or not? What is mean by physically realizable? Physically realizable means, what is Z power minus 1? Z power minus 1 means previous value. Suppose E of Z, before that one Z power minus 1 is, means previous values of controller output. Y of n minus 1. Previous error means E of n minus 1. Z power minus 2. E of Z means it is 2 sampling period before. It means E of n minus 2. Like that we will understand. Suppose the controller you designed require E of n plus 1 it requires. It means what? It requires a future value. It requires a future value. So it's not possible to find the future error. That's why it is not physically realizable. So physically future values are not available. That's why it is not possible to find the future value. Such controllers are called physically not realizable controller. Once you designed, you should check whether your controller is physically realizable or not. because if it is not physically realizable, if you try to implement, it expects future value. How to find whether controller is physically realizable or not? How to find that? For that, we have to go for, we have to check the numerator. And the highest power of numerator cannot be a positive. For example, I'm having a controller like this. Here, you take this controller. This controller. Here, what is the highest positive, highest degree? +1. It should not be positive. It should not be positive. That is yes. And now you come here. What is that highest? It is positive. That's why it is not physically realizable. You check whether it is physically realizable or not. How to find that? We should we should we should find the controller output. Yeah, C is the controller output. C of n we have to find. For that, you cross multiply. So C of z multiplied by C of z multiplied by the denominator comes to the left. 1 plus 2 z power minus 1 plus 2 z power minus 2. You bring this to the right hand side. So what you will get? E of z right hand side and the numerator term. Z power +1, Z power -1, Z power -2. If you put like this, then you multiply, then you see multiply and find the Z inverse. What you will get? You will get C of Z multiplied by 1. You will get C of n. C of z multiplied by 2z power -1. One delay, one sampling period delay. That's why 2 multiplied by C of n minus 1. Then C of z multiplied by z power -2. C of n minus 2. C of n minus 2. That you got. So then the right hand side, what you will get? E of z should be multiplied by z power 1. E of n plus 1. Future error required. If you multiply this E of n minus 2, if you multiply this E of n minus 2, here everything is available. Everything is available. This is available. Nth sampling instant. This is available. This is available. Old value. This is available. Old value. This is future value. Not available. But this is old value available. This is old value available. This is future value. That's why not available. Not available. That's why it's not physically realizable. You cannot implement this. If you try to implement, you bring all C of, you keep C of n alone in the left hand side, bring all to the right hand side. This is what previous controller output, 2 sampling period before the controller output, 1 sampling period before controller output. Both are available. If you have a memory, it can be stored and it can be retrieved. This is what error before 2 sampling period, error before 1 sampling period, all are available except this. What is this? Future error. That's why it's not physically realizable. Here, one may think that, sir, let us multiply the numerator and denominator by z power -1. Then what will happen? This becomes 1. Z power -1, if you multiply, then controller output, you can the controller output become, if I multiply the numerator and denominator by z power -1, what you will get? Z power -1 multiplied by z power +1, 1. Then if you multiply this, what you will get? Plus z power -2 plus this is what? -2, sorry, -2 z power -3 it becomes, because we are multiplying by z power -1 numerator and denominator. So here z power -1 plus 2 z power -2 plus z power -3. Sir, no positive power, sir. Will it work for, will it be realizable? No. What happens? You can directly convert, multiply the, what we did, multiply the numerator and denominator by z power -1. It means what? Every term is multiplied by z power -1. All terms multiplied by z power -1. Then what you will get here? C of n -2. instead of n minus 1, you will get n minus 3. So yes, it is available. Here what you will get 2 times c of n minus 2, n minus 2, because all terms must be multiplied by z power minus 1 to make this positive. To remove this positive term, I multiplied the numerator by z power minus 1, denominator z power minus 1. Then what I am getting is what I am getting is here c of n minus 3, here minus 2 c of n minus 2, because we are multiplying this also by z power minus 1. If you multiply this also by z power minus 1, minus 2 is e of, this is error, this is controller output. These two are controller outputs, fast controller outputs. E of n minus 3, this is also available. Then this becomes e of n minus 2, this is also available. This becomes e of n, yes, this is also available. So if you multiply every term by z power minus 1, sir, it's available, then it's working. Yes, it's working. But what happens to the left? It is c of n minus 1, not n. So every term must be multiplied by z power minus 1. It is previous controller output, it's not present controller output. That's why if the controller has how to check, sir, how to check, then you should check the denominator must have a constant term. Like that you would adjust this z. The denominator must have a constant term. Like that, if you adjust, if this constant term comes here, you will get automatically c of n. Automatically you will get c of n. Therefore, we have to adjust the denominator so that it has one constant term, then you cross multiply. It is given as such, that's why we didn't do that any adjustment here. Otherwise, it will not be physically realizable. So, when and all this situation will arise, that we'll see now. When and all you will end up with physically not realizable controllers, that we'll see now. When you will get physically not realizable controllers. Suppose your system has a dead time of 2 sampling period, you considered it as only 1 sampling period. Dead time is 2 seconds, you consider it as 1 second. In that case, you will end up with not physically realizable controller. That is one thing. So that is one thing. If dead time is there in the system, but you are not considering that exactly equal amount, then you will end up with physically not realizable controllers. Physically not realizable controllers. So if you end up with the physically not realizable controller, means what you have to do is you have to redo the design procedure where you did mistake. You have to think how much. Suppose you are end up with z power plus 1, means if you adjust 1 sampling period in the design, then you will get physically realizable. Suppose you are having a physically unrealizable, but z power 2 means you have to adjust 2 sampling period. Like that, you can directly get that idea. Then we will move on to deadbeat, design of deadbeat controller. Already we have seen this in the class, but once again, for completeness, we'll see that once again. But in addition that, this will be the examination point of view. There it is lab point of view. Earlier you saw deadbeat algorithm, the lab point of view. Now we will see complete deadbeat algorithm for the examination point of view. And to understand deadbeat algorithm, that is also there. Now, what is deadbeat? How to design deadbeat controller? Already we have seen that digital controller is d of z equal to 1 by hgp of z. It is nothing but the mathematical model of the process. If you know the mathematical model of the process, then we will get hgp of z. No. How to get the mathematical model? Take the process. Earlier I thought of telling that I deviated. Now we'll see that. How to get the mathematical model of the process is not available, then what you have to do? You have to do that. We have to take the process. Its mathematical model is not available. Give a small step change. Then you will get the response like this. This is step change is given. You will get the model as kp e power minus dead time in that class TDS upon TPS plus 1. If you get this model, you do not know about, you know nothing about this model, but you have the response for step input. You have the response for the step input means this is sufficient to design the controller. This is sufficient to design the controller. If you know that model, then it is sufficient to find HGP of Z. That's all. Then what is required in addition to that? You need the ratio of Y of Z by Y set point of Z. If you know that, you can find the digital controller. So in the deadbeat algorithm, what we are assuming that Y of Z by Y set point of Z is known. Y of Z by Y set point of Z is known. If you, how it is assumed, what is Y of Y set point of Z? A step change. Let us assume that a step change is given. This is Y set point of Z. Y set point of Z. What is Y of Z? We are expecting that. Can we expect response from here? No. When we will observe in digital discrete system, suppose we give input here means the response, if, definitely after this input only it will come. Here it will come. It is not visible for discrete time system. It will available only from here. Now let us assume that after giving input here, the response comes like this. The response is like this. That is also a step response with the if I give, this is Y set point of Z, this is Y set point of Z, Y set point of Z is given, then the response is like this. So after a delay of one sampling period, we are getting Y of Z like this. I want to dictate the process to change set point change. The temperature is 80 degrees centigrade. I want to change it to 90 degrees centigrade. Now, therefore, the set point is changed from 80 to 90. 80 to 90. So process also follows that 90 degree, but after one sampling period. Because it comes here like this, let us assume. But this part is unknown to any discrete time system. We will know only at sampling instance only we know. Here we got the output, that is the set point equal to set point and remains in that value. That is the assumption we made while designing the deadbeat algorithm. Therefore, step change is given. Unit step change is given. Therefore, what is the assumption made in deadbeat algorithm? Y set point of Z equal to, what is a step function in discrete domain? 1 by 1 minus Z power minus 1. What is the response? Response also 1 by 1 minus Z power minus 1, but a delay with a delay of Z power minus 1. The delayed step response. The delayed step response. This is the delayed step response. That is step response. What is the expression? 1 by 1 minus Z power minus 1. Delay by one sampling period. That's why Z power minus 1. So this is the response. Now to design the digital controller, what is required? Y of Z by Y set point of Z. That is equal to, if you divide Y of Z by Y set point of Z, you will get Z power minus 1. You will get Z power minus 1. So therefore, the controller is 1 by HGP of Z, Z power minus 1 divided by 1 minus Z power minus 1. Then what is left out? Only we have to find HGP of Z. If you find HGP of Z and substitute here, you will get the deadbeat controller. So now we will now let us design a deadbeat controller for a first order process. First order process is given 10 upon 0.5s plus 1. That is given. For that, what it is a continuous time system, so we cannot give directly discrete input. That's why it is multiplied by uh, zero order fold, and then therefore it becomes HGP of S. If you take Z transform, it becomes HGP of Z. So what is 1 minus e power minus ts? That is 1 minus z power minus 1, 1 minus z power minus 1. And for 1 by s into s plus 1, if you take z transform for that, you will get like this. That is, there is a ready-made formula is available for a upon s multiplied by s plus a. For that, ready-made formula is available. That's why no need to do partial fraction. You can use this formula. You can use this formula. You can use this formula to find the Z transform. That's why no need to. If you memorize this, that is sufficient. If you memorize this, you will get. So if you see here, we'll see all this later. What you will get in the denominator, if you find the Z transform for 10 upon S multiplied by 0.5 S plus 1, if you find in the denominator, you will have one more term, 1 minus Z power minus 1 will be there. But that is getting cancelled with this term. And that is getting cancelled with this term. This term also you 1 minus 1 minus Z power minus 1. Here also you are having multiplied with this 1 minus z power minus 1 from the formula. That's why this and this z transform of this getting cancelled. Therefore, you got this is the z transform for HGP of z. Now you got HGP of z, you got substitute in the d of z 1 by HGP of z. That's why what you will get is, what you are getting is 1 by HGP of z. This is HGP of z, means 1 by HGP of z, this. Then what is the y of z by y set point of z? So z power minus 1. Y of z by y set point of z. Y set point of z by y of z. Y of z by y set point of z equal to z power minus 1. Y set point of z is minus 1. If you substitute all these things here, you get the controller. You get the controller. Whether this is no positive powers of z in the numerator, that's why this is physically realizable. If you realize that, you will get C of n equal to C of n minus 1. What is that? This is the controller. This is the controller. If you cross multiply, you will get C of n for this one. For this z power n minus 1, minus is there. Here, that's why C of n minus 1, if you cross multiply this, equal to 1 by 8.6. And what is here? If you multiply E of z and bring here E of n, for this one minus 0.14 z power minus 1 E of n minus 1. Previous error, that's all. This is the controller output. If you bring this to the right hand side, you are getting this expression. What is this controller output? C of n equal to C of n minus 1 plus 1 by 8.6 E of n minus 0.14 divided by 8.6 into E of n minus 1. That's all. So this can be physically realizable. It doesn't require any future value. Therefore, this is physically realizable. Let us stop here. Tomorrow we'll once again see the deadbeat algorithm, and it's these things are we have to see about deadbeat algorithm for theory aspect. That and all we'll see tomorrow. Then we'll see Dahlin's method. Then we'll compare Dahlin's method and deadbeat. Then what is a ringing in controllers? We will see ringing effect in controllers. Then we'll see how to eliminating the ringing effect. That's all I prepared for today's class, but want of time we finished.